Hello and welcome to this video about matrix data structures. In this video, we'll learn how to create the matrix image function in JavaScript that can get the image of a matrix. This can also double up as the column space of a matrix. We'll also create a function that can generate a random vector that's inside the image of this matrix, and another one to test whether or not a row vector is in the image of this matrix. So we'll start by defining what the image of a matrix is. It's all of the possible products of this matrix when multiplied by a column vector on the right. So here's an example of such a matrix. A is a square matrix with a column of zeros in the middle, and we'll try to find the image of this matrix. We'll get it into reduced row echelon form, and then look for all of the pivot columns. These columns are all zeros, with a 1 in the correct position. The next pivot column has a 1 in the next lower position when compared to the previous pivot column. So we see here that all of the columns are pivot columns, except for the third column. So this matrix called the image of A or ImA contains all of the columns in A that correspond to the pivot columns in its reduced row echelon form. So we just deleted out all of the free variable columns, like the middle column. This is a good way to store these vectors, because they can be separated out and treated separately, and are stored compactly. And so the next thing we have to do is to get the Gaussian matrix of the image matrix of A, when we treat the image of A like a matrix. This matrix doesn't really have an inverse, because it isn't a square matrix. But it does have a matrix that can be multiplied on the left by it to give its reduced row echelon form. I didn't know what to call it because it isn't an inverse, but then I decided to call it the Gaussian matrix, because it represents all of the row operations used to get it into reduced row echelon form. So I've used this equation to represent this. And in our example, this is what this Gaussian matrix is. I've chopped off a lot of its extra decimal places for each entry to make it easier to read. Now to write our first bit of code so as to get the image of A called ImA, and we can get its Gaussian matrix as well. We'll declare the function and all of its interior variables. We'll declare the function and all of its internal variables. We'll store the matrix A into C, because using the reducing function on it will destroy it. Then we'll transform it into reduced row echelon form. We'll then search out all of the pivot columns in this matrix so as to get the right columns of A to put into it. We'll create this loop to look at each column. We'll assume that each column is a pivot column until we can find an exception. We'll loop through each entry in this particular column. There has to be a 1 in the correct position, otherwise it isn't a pivot column. And there has to be a 0 at each other position, otherwise it isn't a pivot column either. If it is a pivot column, then we'll add this onto the pivot column list. It's indexed here by K. Then we can set these global variables. The rank of A is equal to the number of its pivot columns. Its nullity can be found here too. Now we have to retrieve the matrix A so that we can calculate the image matrix from it. We'll loop through all of the pivot column locations that we found. We'll get the ith pivot location here. We'll make a loop to copy the column of A corresponding to this pivot column that we found. This is where we'll copy each entry from the matrix A into the image matrix ImA. Now to get the Gaussian matrix of ImA, we'll copy it to A so that we can get its reduced row echelon form and also its Gaussian matrix. We'll reduce it here. The Gaussian matrix should now be located in B. We'll copy this Gaussian matrix into the matrix GS, which is short for Gaussian. Then we'll retrieve A again from C. Now for a bit of theory about how to get a random vector in the image of A. We'll suppose that B is in this image, and this is what the image of A looks like as a matrix of column vectors. Then B will be in this form, where the r's are scalars and can be calculated randomly, and the a's are the column vectors in the image. Then for our example, b will be the sum of these vectors like this. Now to write a function that can calculate a random vector in the image of A, we'll store this vector in B. It's a column vector, so the number of columns is set to be 1, and its rows are set to be those of the Gaussian matrix. We'll reset B to be 0. We'll create a loop to look at each column in the image of A separately. We'll set R to be a random number with 1 decimal place, and R won't be 0. We'll create a loop to copy every entry in the column of Im A into B. We'll get the locations in these matrices here, and we'll do the copying here, adding R times this column vector to B. So I'll just show you the Gaussian matrix of the image of A here again. And I'll just show this calculation showing how to get a random vector in the image of A. We can pack this vector equation up into this matrix equation. We can pack this equation up into this more general form of matrix equation. So B is in the image if a variable R like this exists for B. This is the equation that we'll be working with. So I'll want to change the vector from R to A. This is the equation of the Gaussian matrix. It multiplies on the left to give Im A in reduced row echelon form. We'll see how to use this to test if B is in the image of A. We'll set B to be this for some A, that's any vector in Rn space. In this example, that it's any column vector with 4 elements. We'll multiply the Gaussian matrix on the left on both sides of this equation, and the right side should have a matrix that looks like this. I'll just substitute the Gaussian matrix in this example into this equation, and expand out the vectors A and B. Simplifying the right-hand side gives us this, the vector A with a 0 attached to the bottom. So multiplying the vector B by the Gaussian matrix on the left should give us a vector with 1 or more zeros at the bottom like this, if it's in the image, and this is what we'll have to check for. Now to write out the function to tell us whether B is in the image of A. We'll set the main return variable to be true until we can find an exception. We'll multiply the Gaussian matrix by B, the vector we're testing to see whether or not is in the image, and place it into C. We'll round C so that very tiny numbers will be made equal to 0, so that the testing mechanism will work properly. We'll loop through all of the bottom section of C that should contain all zeros. This is the location in C that we want to look at. And if the number found here isn't 0, then this vector isn't in the image of A, and we can jump out of this loop straight away. And here is where we'll return the main return variable, saying whether it's true or false. And here's the main testing function. I'll firstly get the image matrix and its corresponding Gaussian matrix using this function, so that I can use the other functions. And I'll loop through 10,000 different random vectors for B. It does go a lot quicker than it looks. Then I'll create the random vector and test it here. It should return true, so I'll only print out something if it returns false, and therefore not working properly. And I'll print out something here so as to make sure that this testing function is working properly. I'll do the same thing here, only to test whether this function can correctly determine whether a vector isn't in the image. Adding this small number to the first element of B should do this, but only if this itself isn't in the image of A. So I hope that you have found this video helpful and insightful. Please click like and subscribe if you did. Please leave some helpful thoughts in the comments. Feel free to share this video. And thanks a lot for watching.